We're now ready to talk about nonlinear SVMs. And the really nice thing is from the hard linear SVMs separable to the soft SVMs non-separable to the nonlinear SVMs, the code is going to stay the same. And we're not going to do a full derivation of the nonlinear SVMs, but I'm going to give you the intuition for it. So here's the basic idea. In all the toy examples that we've been doing, there's been a separation, maybe a few data points moved from one side to the other, but there has been more or less this notion of a linear separation. That is, I can draw a line or a plane or a hyperplane between the data to build my classifier. But that's not always going to be the case. So for example, here you can see I have this very nonlinear surface. The data is actually pretty separable. Yeah, there's this little quadrant down here, but try to draw a line in this space and figure out how well you can do. Well, it's going to be pretty hard here because the surface is actually quite curvy here. And so now the question is, well, how do you build classifiers for this? And so what nonlinear SVMs do with a soft margin, again, of course, because there's going to be misclassified data, is it sort of looks very similar. Look what I'm doing here. I'm maximizing the margin, so I'm minimizing the inverse of the margin. Plus, there's my weight C with my slack variables that we saw before. And below, I have something that looks pretty similar. I have my class label Y. I've got W times, there's something new there, phi. Ignore that for a second. W times X, that's the dot product, plus B should be greater than 1 minus epsilon, there's my slack variable, such that epsilon is always greater than 0 for all I. So everything here is exactly the same as before, except I've introduced a so-called kernel function. This is the nonlinearity that is going to try to learn a more complex separation between the classes. By way of intuition, think about this problem right here. So if you wanted to build a classifier here, I think we can all agree this is the mother of all nonlinearly separable problems, because pick any slice through here and you're going to have a lot of problems. But there is a separation, which is this dotted circle. And what would a good nonlinearity or mapping or kernel function look like? Well, if I took this data, x, y, and I converted it to, say, polar coordinates from rectangular coordinates, where I now am parameterized in terms of radius and angle, what would happen to this data? Well, all the red dots would have a small radius, but spanning all the orientations. All the blue dots would have a big radius, spanning all the orientations, and they would be linearly separable down the middle. The red is near the origin, the blue is away from the origin. And essentially what nonlinear SVMs do is they play with different types of kernel functions, nonlinear mappings, to try to learn that separation. So that's the good news, is that you can learn these separating surfaces. The bad news is that the optimization is significantly more complicated. And then the good news is the libraries that now do these optimizations are doing a pretty good job of searching over the various types of nonlinearities to get you a good classifier. And here's an example of the code and the result for that. So we're going to play the same game here. We've got a bunch of data. I'm now going to call SVC. I've got still 10 on my slack variable. And now the kernel, instead of being linear, is an RBF, which stands for radial basis function. There are other kernels. There's polynomial kernels. And if you look at the documentation for SVC, you'll see there are different kernels that will give you different performance depending on your data set. Now, it turns out that within the RBF, you have to make some decisions, which I'm not going to talk about here because we simply don't have the time to get into the nitty-gritty of the optimization. But when you call this SVC, it is actually doing a search over various parameters associated with this nonlinearity to give you good classification, as you see here. And here is the result of the classifier. So what am I showing you here? I'm showing you, again, in red is one class, and in blue is the other class. Here's the separating surface that I've rendered for you. And I've, again, color-coded the data according to confidence. Yeah? And you can see that when you have these bright colors, you have high confidence, and when you have bright hues, rather, and when the hues go closer to white, you have lower confidence. And notice something interesting here. Along the margin, that dashed line, you're not as confident. But also notice that as I move away from either side, I'm not as confident either because I don't have support there. So what these nonlinearities are doing, in this case the radial basis function are doing, is they are learning a mapping in a higher dimensional space. And then when we come back down into this dimensional space, there is essentially a support for where your data is. And when your data deviates from that in any direction, you have less confidence in its ability to classify correctly because it doesn't look like the training data. And that makes really good sense. Okay, so the good news is that these SVM libraries, by just playing with these kernels and playing a little bit with these weights, and look, don't let anybody tell you otherwise. There is some black magic here. There's a number of parameters that need to be tweaked and searched over, and this can be very, very slow compared to linear discriminant analysis, compared to linear SVMs, compared to logistic regression, because you have to search over spaces to do these optimizations. And the optimizations themselves have some pretty interesting and gnarly details, which we will not get into here because at the end of the day, this is not an optimization class. All right. But this is good news. We now have a little bit more machinery. We have a bunch of machinery for doing linear classifiers, and we have some machinery for doing nonlinear classifiers to deal with more complex data sets. This is incredibly important. There is this tendency today to, when you have a problem, to go grab the most powerful tool on the shelf and throw it at the problem and hope for the best. And that's a really bad way to do science, and it's a bad way to do engineering. The problem should be, the way you should approach this problem is take the simplest tools you have. Don't reach for the chainsaw, right? Grab the scissors and see how well your problem is behaved. See how well logistic regression works. See how well linear discrimination works. See how well linear SVMs work before you pull out the nonlinears. Why? Well, first of all, the nonlinear stuff is complicated, it's computationally demanding, and if you get a result there, how do you know you needed all that machinery? You need to know that if you take these very simple techniques, I'm going to get a certain performance. And then when you go to do the nonlinear techniques, you have baseline. You can say, look, this improved relative to the linear, or it didn't improve, which means my problem is not about the separability of the problem, my problem is something completely different. And so it's always good to start with these simple tools and work your way up. And eventually we're going to start adding more machinery here and more complexity, but there is a spectrum of these techniques. The linear techniques may be less powerful in terms of performance, but they are simple, they are efficient, and they're easy to understand. And then we have degrees of that, and you should always work your way up from the simple tools to the more complex tools.